Okay, hello Cloud Gurus and welcome to this lecture. In this lecture, we're going to take a tour through all the different Google Cloud Platform services that are about storing data, and see how you can transfer a lot of data into some of those services. Now this is one of the longer groups of services, so you might want to have a coffee in hand. Also, remember that in Google Cloud Platform, data is always encrypted at rest, so nothing that we're talking about in this lecture ever gets saved to any drive as plain, understandable data. So with that said, let's take a look at the first service. Let's start off with local SSD. In GCP, a mention of local SSD is talking about the very fast 375 gigabyte solid-state drives that are physically attached to the different servers. In the AWS world, this would be the EC2 instance store volumes, and in your own data center, this would be direct attached storage. Now I've marked these as zonal resources, but really they're even more specific than that. They're attached to a single specific Google Compute Engine instance. And the main reason you'd want to use these is because they offer incredibly high performance, especially when you stripe across several of them. Now it's very important to note that all data stored on a local SSD drive will be lost whenever the instance shuts down, whether that's on purpose or not. But it is pretty nice to know that Google does some magic behind the scenes so that they can actually move your instance from one place to another, called a live migration, and this data comes along for the ride. Now, like I've said, all data in Google Cloud Platform is always encrypted at rest, but I think it bears repeating for this service because it's locally attached storage. Now, when you start up an instance with local SSD attached, you'll start paying for the local SSDs for however long you keep that instance running. Next up, we have the Persistent Disk Service, often abbreviated PD. Now this is flexible block-based network-attached storage, and it's the boot disk for every Google Compute Engine instance. Now this is block storage, so you format and use them like a physically attached hard drive, but they're not physically attached. And the data is also encrypted when it's in transit between the compute instance and the persistent disk service. This compares to Amazon's Elastic Block Storage or a storage area network in your own data center. The larger the volume is, the faster these drives get. Now their maximum performance is way below the local SSD performance, but it's still fast enough for most uses, up to 40,000 read IOPS on a single instance. Now the really nice thing about persistent disks is that they persist, and they're replicated for durability. Unlike local SSD, these can stick around even after you shut down the instance, and you can reattach them to a new instance in that zone. Now you provision a certain size up front, but you can resize them while you're using them and make the drives quite large, but you will need to update the file system within the VM to be able to take advantage of that extra space. Now persistent disks also allow you to take snapshots and make machine images out of them, and that adds even more capability and flexibility. Now these snapshots are what you might call magical. When you do take a snapshot of a drive like this, you only pay the incremental time and storage cost, but you can use or delete any backup like it was a full backup. If you delete something that's the basis for another incremental, Google will automatically behind the scenes move the data into the next incremental so that nothing is lost. And if you do a restore from any one of them, it'll automatically gather up all of the right information without you having to do anything. Now, even though persistent disks themselves are zonal resources, snapshots are automatically available globally, but you will pay network charges if you read them cross-region, so it's unfortunately not a way to bypass the network egress charges. Now this is not file-based network-attached storage, it's block-based, but you can mount one persistent disk to multiple instances if all of them are mounted read-only. Unfortunately, that means you can't update it while it's in use, but there are some circumstances where this could be valuable functionality. So when you're provisioning one of these, you can choose a performance class, and then you'll pay per gigabyte for however long you keep that persistent disk around. Same goes for snapshots. When you take a snapshot, you'll start paying for however much data is stored in that snapshot for however long you keep it. So with persistent disk and local SSD, you could definitely install your own database on that. If you installed it on local SSD, you'd get really high performance, but you'd have to be a lot more careful about data durability. And if you installed it on persistent disk, then you can take snapshots more easily, but it's still a fair amount of work to manage. So if you want to store some data in a SQL database, you should probably take a look at Cloud SQL instead. Cloud SQL is a service for fully managed and reliable MySQL and PostgreSQL databases. This compares to Amazon's relational database service, and if you were doing this on your own, you might do like I was just talking about and manage the MySQL database yourself. The nice thing about Cloud SQL, though, is that it supports automatic replication, backup, and failover, and a bunch of other database management things. Now, if you need to scale a Cloud SQL instance, you have to do that manually, whether you want to make one Cloud SQL instance more powerful or whether you want to attach replicas. Now, it's not quite this straightforward, but you basically wind up paying for the underlying Google Compute Engine instances and persistent disks, plus some extra service fees for them to manage the Cloud SQL database for you. But let's say that you've outgrown Cloud SQL. What would you use instead? Well, that's where Cloud Spanner comes in. According to Google, Cloud Spanner is the first horizontally scalable, strongly consistent relational database service. Now, if you were doing this on your own, you might wind up using sharded MySQL instances or CockroachDB. Now, it says here that it's strongly consistent, but actually Spanner provides external consistency, which is incidentally stronger than strong consistency. Now, that means a lot more to people who spend all day long thinking about databases like this, but what it means for you and me is that we can use Cloud Spanner like a normal SQL database without having to give up some of the ACID guarantees that we're used to just because the database is so huge. And when I say huge, I mean huge. This can scale from 1 to hundreds or thousands of nodes. And Google recommends that you have at least 3 nodes for any production environment. Now that said, even with a single node, the data is very durable with lots of replicas. Because a node is not actually a single server somewhere, a node is a server in each of the replication locations. Now, one more thing about the consistency. If you are willing to give up some of the ACID guarantees, then if you want to be able to read the data with the lowest possible latency, Cloud Spanner offers something called stale reads, which are also stronger than the eventual consistency you might get from a NoSQL database. Now, some of you might have heard of the CAP theorem, which effectively says that for a system like this, you can choose at most 2 of consistency, partition tolerance, and availability. And so the way that Cloud Spanner gets away with such strong guarantees about consistency and still keeping partition tolerance is that it gives up 100% availability. But this is still a very, very high availability system. The service level agreement has a 99.999 service level objective. 5 nines when Cloud Spanner is deployed as a multi-region instance. That's insanely good, really. And if you think about it, nothing is actually 100%. So this seems like a pretty reasonable trade-off. There's a great page that talks about the Spanner instance configurations. Now this uses some pretty impressive and innovative technology, and it manages to improve the performance a bit further by using a private GCP region in Oklahoma in the central USA. Now it's interesting to note here that this system is not based on failover, where requests come into one server and then if that server dies, it takes a while for things to shift over to the next server. It's designed so that any of the servers can handle any of the requests, and that's how they can keep the availability so high. Now, if you want to use Cloud Spanner, you should realize that this is for seriously large systems. This is not the kind of database you'd use for your neighborhood barbecue sign-up app. When you provision a Cloud Spanner instance with a certain number of nodes, and in a certain region or multi-region, you'll start paying until you shut that instance down. And you'll also pay for however much storage time you actually use. Now, the minimum cost for Cloud Spanner instances is relatively high. For a production level setup, you're looking at thousands of dollars a month, and that's only for single region. If you want multi-region, that's tens of thousands of dollars a month. So just for fun, imagine that you were running a global Spanner instance in your system for 3 years with a few thousand nodes to handle ridiculously massive scale, like more than 1 million queries per second. Now, Google would guarantee less than 16 minutes of downtime over that 3-year period, but it would cost you like $1 billion. Actually, if you had 4,228 nodes in this setup, it would cost you almost exactly $1 billion over the 3 years. Seriously. But it's fun to imagine, right? Okay, so let's say you don't need quite that transactional kind of scale. Let's say that you're instead more interested in being able to do lots of SQL-type queries, but not the same kind of concurrent updating. Here's where you might look at BigQuery. Now, many people say that BigQuery is the most significant service in the Google Cloud Platform, so let's take a look at why. BigQuery is a serverless column store data warehouse for analytics using SQL. Now, if you have an AWS background and you see column store data warehouse, you're probably thinking of Redshift. Now, Redshift and BigQuery do share some use cases, but BigQuery is very different from Redshift. In particular, BigQuery is serverless and offers amazing scale without having to provision anything up front. So you could be running no queries whatsoever for a while and paying nothing for those queries, only paying a little bit to store the data. And then all of a sudden you might slam it with a whole bunch of huge queries. No big deal to BigQuery. It scales internally, so it can scan terabytes in seconds and petabytes in minutes. So late in 2016, AWS announced their new Athena service, which is effectively their copy of BigQuery. And as AWS has the tendency to automate things you could do yourself, they based Athena on Presto, which was released by Facebook in 2012. But BigQuery is not based on Presto. It is Google's own innovation that they released as a service way back in 2010, and it uses some really awesome technology internally. If you want, you can read more about that at this link here. Now, when you use BigQuery, you pay for the gigabytes of data that BigQuery has to actually consider or scan during the query that you give it. Now, as I'm recording this, the on-demand pricing is currently $5 per terabyte, so your query can scan 2 gigabytes of data for a penny. Now, very high-volume customers can pay a flat rate for BigQuery slots, but they currently start at $40,000 per month, so they're definitely not for most users. Now, an extra nice thing about BigQuery is that it remembers the queries that you run and the results from those queries. And if you wind up making the same query again against the same data, then it'll just give you the result from its cache for free. Now, the query results are generally cached for 24 hours, and they'll have to be dumped if you wind up changing the tables. Another thing you have to pay for is data that you store over time, but this is actually relatively inexpensive, and it automatically gets even cheaper when you don't modify a particular table for 90 days, even if you read a whole bunch from it. Now, one more thing that gets charged for using BigQuery is when you add data through streaming inserts. There's a per gigabyte charge for that. And streaming inserts can also cost you in that query caches will have to be invalidated. So even if you rerun the same query within the normal 24-hour period for caching, it'll have to rerun the query against the new data. So let's say that instead of using SQL, you're willing to use NoSQL to scale to really high volumes. Well, Cloud Bigtable is a low latency and high throughput NoSQL database for large operational and analytical applications. This is a wide column store type NoSQL database, like Amazon's DynamoDB and Cassandra, but I think the closest you'll get to Cloud Bigtable is Apache HBase, which was made to replicate the Bigtable functionality. And you might run HBase in your own data center or on Amazon's EMR service, where it's natively supported. Now, Google has also added support for the open source HBase API. Cloud Bigtable also integrates well with Hadoop, and also the Cloud Dataflow and Cloud Dataproc services that we'll cover in another lecture. Cloud Bigtable can scale without interrupting its functionality, and the storage just scales automatically as you add more data. If you want to scale the processing nodes, though, you have to do that manually, and you pay for the processing node hours that you have provisioned. You also pay for however much data you store over time, and you can choose to use either cheaper hard drives or faster solid-state drives. But Cloud Bigtable is really made for huge workloads, and if you don't have that level of scale, you might want to consider Cloud Data Store. Cloud Data Store is a managed and auto-scaled NoSQL database with indexes, queries, and ACID transaction support. Now, just one quick note, these transactions are a little bit different than you might be used to in the SQL world, in that if you change some data within a transaction and then reread that same data, you won't see the updated data. In any case, Cloud Data Store would compare to Amazon's DynamoDB service, and if you were doing this on your own, you might wind up managing your own MongoDB cluster. Now, this is a NoSQL database, so the queries can get a little complicated. In particular, you don't get to do any joins or aggregates, and your queries have to line up with the indexes. Also, not all of the operations that you're normally used to are natively supported, so you should take a look at the document I've linked here to read more about Cloud Data Store queries. Now, Cloud Data Store does make some automatic built-in indexes for simple filtering and sorting, both ascending and descending, and you can make manual composite indexes for more complicated situations. But be careful what you specify, or you might wind up having them explode, as Google calls it, which can wind up costing you a lot in performance and processing. With Cloud Data Store, you pay for however much data you store for however long, including the indexes. So if an index explodes and gets very large, it can cost you money here. You also pay for the operations that you actually perform, so you don't have to pay a certain base amount. You only pay when you actually read, write, and delete the data. Next up, I want to mention the Firebase Real-Time Database and Cloud Firestore. These are some really interesting NoSQL document stores with virtually real-time client updates that happen through managed WebSockets. Now, you might compare this to DynamoDB or MongoDB, but because of the client connection that's built in, to actually replace this functionality, you would need machines to be hosting the WebSockets, you'd need some WebSocket servers, and load balance against those with something like the Elastic Load Balancer or Nginx. So this gets quite complicated. Now, Firebase DB revolves around a single, potentially huge JSON document that's located in the central US. Cloud Firestore is multi-regional, and it has collections which have documents, and those documents contain data. So it's got more structure in its hierarchy. So Firebase has a Spark free tier, a Flame flat tier, but for usage-based pricing where you also want to use Google Cloud Platform, you go with their Blaze plan. Now, with the Real-Time DB, you pay more for the data you store each month and the data you download. Now, with Cloud Firestore, you pay for the operations you do, but you pay a lot less for the storage and transfer. Alright, moving on. Let's say that instead of having structured data, you want to store unstructured data, maybe large files. Now you could set up a file server on a Google Compute Engine instance and store the data on persistent disk or something like that. But you should really take a look at cloud storage. This is one of the most important services in all of GCP because it so often acts as the glue between two other services to enable data to flow through the system. Cloud storage is an infinitely scalable, fully managed, versioned, and highly durable object store. Now, object storage in this description compares to file storage or block storage. So cloud storage stores a bunch of objects in what's called a bucket. And that bucket will live either in a particular region or in a multi-region. With multi-regional storage, the data will be stored in 2 or more physical locations separated by at least 100 miles, which can help you satisfy some redundancy requirements you might have. If we compare this to the Amazon Web Services world, this is very much like Amazon S3 and Amazon Glacier, depending on which cloud storage class we're talking about. The name of an object in cloud storage does not affect the performance or scalability. Google has thankfully avoided this unfortunate quirk that Amazon's S3 service has. Cloud storage also supports built-in and custom metadata per object. You can list the objects by prefix to emulate a folder structure in a way. It supports object change notifications so you can link it to other services via a webhook. Also, you can conditionally update objects based on versions. When you turn versioning on for a cloud storage bucket, it'll independently store different versions of the objects, so you can go back to older versions if you need to. But you will pay to store all of those versions while they exist, so you might want to set up lifecycle transitions to expire them after time. Now, Google Cloud Storage, or GCS for short, is designed for 99.9999999% durability, 11 nines of durability. This means that they're really sure they're not going to lose your data. Really, really sure. Now, cloud storage is strongly consistent, which means that even if you update objects or delete them, no requests for that object after the update will ever get an older version. Cloud storage also has integrated site hosting and content distribution network functionality, which means that you can use it quite effectively to build websites without having to manage all of those pieces yourself. So there are several different classes of cloud storage. There's multi-regional, regional, nearline, and cold line. And you can set up lifecycle transitions so that Google will automatically change them from one class to another depending on how old those objects are. Multi-regional is great when you have data that needs to be spread out, either because of the requesters or because of some redundancy requirements you might have. Regional is a little less expensive than multi-regional and offers faster access in a particular location. Nearline is made for data that you expect to access less than once a month, and cold line is made for data that you expect to access less than once a year. Now, the difference between these different classes is mostly in their cost and availability guarantees, not in their latency. All of the classes have a time to first byte that's measured in milliseconds. Another thing to note is that all of these storage classes have the same API, so you can use the gsutil command line for all of them, and you could even use GCSFuse to mount them as a file system. But do be careful with that. Because it acts very differently to something like block storage, the way that programs in the operating system might interact with it can have unfortunate consequences. For example, if you're updating a huge file to add just a tiny little bit of data to the end, GCSFuse will have to download the entire file, save a new copy of the file with the extra tiny little bit of data, and then upload the entire thing back. That could really slow things down, increase your data transfer costs, and perform a lot of operations that you might not expect. Now, this is important because you pay for each operation that you perform against Google Cloud Storage. You also pay for however much data you store over time, depending on which class it's stored as. And if you access data from nearline and cold line storage, you'll pay a per gigabyte retrieval fee for that as well. And don't forget the network transfer pricing. To get your data out of GCP can cost a significant amount. Also, one last thing to call out is that nearline and cold line have minimum storage durations of 30 and 90 days respectively, which just means that you'll get charged for the rest of that storage time if you delete any of those objects early. So let's say that you have a whole lot of data that you want to move into Google Cloud Storage. Well, this is where the Data Transfer Appliance comes in. This is a rackable, high-capacity storage server that you use to physically ship data to Google to have them put in Google Cloud Storage. This compares to Amazon Web Services' Snowball. Now, Google's Data Transfer Appliance is ingest only, so unfortunately you can't get any data out by using this, and it comes in 100 terabyte or 480 terabyte versions. So just to put this in context, if you shipped a 480 terabyte device like this to Google once a week, the overall data transfer would be faster than using a saturated 6 gigabit per second link. But let's say that your data wasn't in your own data center. Let's say maybe you want to transfer some data from something like S3. Well, the storage transfer service will copy objects like this for you, so you don't need to set up a machine to do it. The destination for the storage transfer service is always a GCS bucket, but the source can be S3, an HTTP or HTTPS endpoint, or another GCS bucket. You can set up storage transfer service jobs as either a one-time thing or scheduled recurring transfers. And the service is free to use, but you pay for what it winds up doing. Alright, well that was a tour of all the storage services in Google Cloud Platform. If you have any questions, please let me know. If not, please feel free to move on to the next lecture. Thank you.